there you are. All right, okay, pop it. We're back. I got the case. I couldn't figure it out. There was no options. I had to shut it off and then switch you. Okay, so we're back. I hope that you were able to see that diffraction pattern. And I was using, again, it's easier now to show these to you in the light. These are very thin double slit lines that are right next to each other. Light, there's some double slit. There's three sets of them. I use the middle set in both of those. But light is such a small wavelength that you need very small slits in order to get it to diffract. So the property of diffraction is hard to see with light. You can get the property of diffraction with sound a lot easier. Like, for example, if you are, like, here's the inside the room. Here's my door. Here's the door. It's a threshold, like the door out to the hall. So this is the hall. This is my classroom. And if you're sitting here in my classroom, if I'm out here talking to you, saying, hello, 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 you can hear me around the corner because sound is a very long, relatively speaking, wavelength. It's like typical sound voices are between 1 and 3 meters, all right, depending on, of course, how high or low your voice is. Now, 1 to 3 meters is pretty big for a wave. And so when we have an opening like a doorway, a doorway is about 1 meter wide, and that diffraction from sound going through it will spread out. Because remember, that's what diffraction means. It means the spreading out of light, okay, spreading out, the bending. Well, it's the bending, but it's not the refraction. We're talking spreading out. Spreading out of light is diffraction. And so, or any wave is diffraction when it spreads out. So the sound going through, I can hear somebody around a corner because the opening, the door, will diffract those sound waves. Why? Because they have comparable wavelength. In other words, the wavelength of voice, sound, about 1 to 3 meters, door, about 1 meter, they're on the same par with each other. If you're going to try to see me around a corner, okay, now we're talking light reflecting off of me, bouncing off me, going in all directions. Well, when my light waves get to the door, they're not going to refract, or diffract, get my words right, not going to diffract because light is so tiny. It's so tiny and cute. Yes, it is. Yes, it is. So cute. Yeah, and it's so small, the wavelength of light, that it laughs at that huge opening of a meter wide door. It's just going, you're not going to do anything. You're not bending me. You're not bending me. Goes right through, doesn't bend. That's why you can't see me around the corner, because light doesn't diffract, spread out with such a large opening. If you want to get light to diffract, you need a very small opening. Now, we had a double diffraction slit. These are double diffraction gratings. Go back here again. And there it goes. And these are double. Each one of these pairs are 2 of them. Of course, with 1 of them, we get the same thing. We get a diffraction, but it has to be a very small opening to diffract light because the light is so small with its wavelength. Okay, so the phenomenon of diffraction is spreading out around a barrier or through an opening. That's spreading out beyond that opening. Now, here's what Young did. Young did what's called the double slit experiment. And Young noticed that phenomenon, which I was giving, of course, he didn't have lasers back then, but still light will do this. So what we do is we're going to draw out what happened. We're going to draw out with the double slits and the light going through it from the laser what happened. Okay, so let's see. Okay, so here is my film with the 2 openings close together. Get you a little closer here. See that a little clearer? Okay. And now I held this up in front of a laser, and then, well, geez, probably about, well, count it out. 1, 2, 3, 4, 5, 6, 7, 8, 9 feet. 9 feet away, I had a piece of paper up taped to the wall. Actually, it's been up there all year since last year, and nobody ever asked me about that. Nobody said, Mr. Cunningham, why do you have a piece of paper stuck to your wall? Nobody asked me, but it's been there all year. Okay, well, now we know. Now we know why. So now that piece of paper on the wall is where we see the diffraction pattern. Why is that? Why do we see that? Okay, here's what's going on. When light goes through these openings, Okay, light goes through. It's an opening, and it's such a small opening. It's a very thin opening. Well, it's thin enough that it can actually begin to diffract the light. It's comparable to the wavelength of the light, like the sound, the door, big, can spread it out. So we get the spreading out. So here's one opening, and that light going through this opening here, okay, spreads out. Oh, those are not very even, okay? That's what coffee does to you, you know? You get all energetic and pumped up, but you can't draw straight. And then with the other opening, the light goes through that one, and it spreads out. So we'll spread the light out through here. Like so. So here's one from that one, here's one from this one. All right, so what you end up doing is you have diffraction occurring through both openings. And when the light spreads out like that, it begins to overlap. And each one of these represents, let's say, a crest of the wave. So each line is the crest of a wave. So we have the crest and the trough and 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 so on. And so every time that we see a crest meeting another crest, something magic happens. So we're interfering. Ooh, there's another word, another property of waves, interference. Okay, you know what interference is. It's a 2-minute minor penalty in the sport of hockey. Interference. You, get in the timeout box. You've been bad. Okay. Yeah, it's pretty good if you get hockey. Okay. Nick gets it. Oh, Nick gave me this. Nick, you're the man. Okay. And he's a hockey player, so he gets that joke. It's funny. He's probably laughing right now. All right, so what I'm saying is that when light goes through and spreads out, this crest is going to hit this crest from light going through here and spreading out. So we get this pattern. I didn't draw it very straight, but if you can see, I kind of lost it there. Crest, 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 crest. All these crests are overlapping along that line, and here, crest here, I kind of didn't draw it straight here. I should have took my time. But we get these crests overlapping through here. And when that happens, when you get one crest overlapping another crest, you get a lot of toothpaste. Crest overlapping another, you get a lot of toothpaste. It's, okay. Fine, okay? Fine, yeah. I'm trying. You people don't appreciate me, do you? So when you get crest and crest going together, you get what's called constructive interference. So you get a wave of one, and the crest of one wave, and the crest of another wave, and they go together, they go boom. That's called constructive interference. And if we get reverse, we get destructive interference. So there's constructive and destructive interference. And so when we get these overlapping places, we get constructive interference. And then we get overlapping in the troughs as well. We can actually get what's called destructive interference. So with this double slit, we get this pattern of constructive and destructive interference. And it's going to show up on the, well, I put a piece of paper. It'll show up on whatever you project it onto, like my piece of paper. So we end up seeing, I'm going to clean this up a little bit for you so we can see on the back. So here's my piece of paper. What ends up happening is with the constructive interference line, you get a bright spot. B for bright. With the destructive interference, where the troughs would overlap, I get a dark spot. Well, actually, it's not a spot. Doesn't make any sense, right? That's like an oxymoron thing there. Dark spot. So you get an area of dark. Right down the middle between these, so I got to make that a little smaller here. Right down the middle between, we get an overlapping pattern where we see a bright spot. That was the brightest spot. So that was right down the middle. You saw that big bright spot in the middle, and then we saw a dark on either side, and then we got a bright spot again. Not as bright as the middle one, though. And then dark, and then bright again. Still getting less bright, but we get dark, bright on either side. And dark. So this is like the bright light. Again, Gremlins, watch it, it's a good movie. And then we get a bright, not as bright as this one, but you notice the other thing I hope that you might have noticed, and go back and watch that video again, is that on each side, the bright spots that appear, the alternating bright spots, are equidistant on either side. from the other bright spot. So we have a bright spot in the middle. It's actually called the maximum. We'll talk about that shortly. The maximum. And then from here, we get a bright spot and a bright spot equidistant away. We get a second bright spot here, equidistant from the other bright spots on the other side as well. Okay? Becoming less bright as we go farther away because the light is beginning now to spread out. Okay, that's a phenomenon of light called the inverse square law. And it gets less and less. You know that. Light bulb. You stand up to the light bulb. Put a light bulb in front of your face. Point it out. You go, ah! Whoa! And then, get 20 feet away. You're nothing. You're nothing now, are you, Mr. Light Bulb 20 feet away? You're nothing because it's not as bright. All right, so now we get this pattern, this repeating pattern, called the diffraction pattern. Young knew this, and he said this can only happen with waves when they constructively and destructively interfere with each other as the crests pass over each other. And if you get a crest and a trough passing over each other, that's where you get the destructive. So, yeah, that's the explanation of how come you get this pattern. Is because of these waves spreading out, you get crest, crest, big, amplified, bright. And when crest, crest line hits the back, you get a bright spot. If you get a crest trough, a crest from one and a trough from another, then what you get in the center of those two, you get a destructive interference pattern because they cancel each other out. And that's where on the back, you get a dark spot. Alternating light and dark spots. Interesting phenomenon. Okay, now, I showed it to you. Try to explain it on the board. Now I'm going to give you another video that has better animation. Animation. Animatronics. How's that? I made that up. I don't know if it's the word or not. They get videos on this. Do a better job with the animation than I'm doing here. And well done and well measured out, so you want to watch that video that I load in for you on how this works. So that's my explanation for it. It's not just mine, it's how it is explained. But you can get a better one from YouTube, and I'll load one in for you, because I'm boring anyways. I'm just boring you right now. You're probably all sleeping and turning me off at this point anyways. All right, so we need to do the math, though. We need to do the math, and that's the next video. What to do with this, and what math are you talking about? All right, back.